Okay, so I will revise first some things because this is a very demanding chapter. We are almost close of it, this balls and boxes. So first I will introduce some notations. So if you remember, notations were fmn. Fmn was symbol for n to the power m, this big expression n choose 1, n minus 1 whole to the power m plus n choose 2, n minus 2 whole to the power m plus minus, it is going on. I can write in sigma form. That will look more drastic, but then okay. So this is n choose I can write k and n minus k to the power m. This is all m only, and minus 1 to the power k, and k equal to 0 to n minus 1. It will look like in sigma form. I recommend that you remember this form. This is easy because anyway, to evaluate you have to develop. Okay, so this is just writing this one k 0 to n minus 1 because anyway when k equal to n, things will be 0. So to stop there. So this fmn was that was number of on fa to b number of onto functions. This was number of onto functions where size of set A was m and size of set B was n, or cardinality of A is m and cardinality of B is n. So so number of onto functions from a set having m elements to a set having n elements is given by this big expression, which is obtained using pi, and that explains why you have got sign positive, negative. It is called sometimes alternating sum. This is called sum, alternating sum. Alternating sum means something that keeps on changing positive and negative. So this is expression is alternating sum, so which resembles pi. This is also equal to number of ways to put m distinct balls. Because function is there, so it can't be identical. M distinct balls into n distinct boxes. So it's ball and boxes problem, that m distinct balls into n distinct balls are fmn. Okay, some things were that yesterday we did f53. Number of ways to put 5 distinct balls into 3 boxes was 150. That we got f53. We can also calculate many other things. Two things worth noticing is fnn. Suppose m equal to n. Fnn, that is n to the power n minus n choose 1, n minus 1 to the power n plus n choose 2, n minus 2 to the power n, and minus so on. That number will be n factorial. Why? Because it is actually you are saying that I want an onto function from a set having n elements, say set having 4 elements to set having 4 elements. So it has to be 1 1 as well. If it is onto, it has to be 1 1 as well, and that means that it is actually bisective. So it is just like matching problem, that 4 people, say 4 people and 4 persons and 4 chairs, so they can sit on chairs in factorial 4 ways. So if you do it, will get this. For example would be anything you can take. Suppose I take some small example, 3 to the power 3 minus 3 choose 1, 2 to the power 3 plus 3 choose 2, 1 to the power 3. This should be factorial 3. You can check that. If I take 5 to the power 5 minus 5 choose 1, then 5 choose 1, 4 to the power 5 plus 5 choose 2, 3 to the power 5 minus 5 choose 1, 2 to the power 5. No, 5 choose 1, 5 choose 2, 5 choose 3 to the power 5, and plus 5 choose 4, 1 to the power 5. If you calculate that, you should get factorial 5, because left side calculates number of onto functions from a set having 5 elements to a set having 5 elements, and right side is just the number of 1 1 functions, or say number of bijections, that is factorial 5. So this you will get. This is one thing. Other thing is that fmn is 0 if m is less than n. Means if you have got number of balls is 3 and boxes are 8, then it can never be an onto mapping. For onto, you know that m greater than equal to n, m greater than or equal to n. So it is 0. It means this expression, this m to the power n, this expression, that is n to the power m minus n choose 1, n minus 1 to the power m plus n choose 2, n minus 2 to the power m, and minus this thing. It's interesting, very interesting. This will be 0 if you choose. This is just algebra, that if you choose this one, if you choose m less than n, this will be 0. So one example could be this. One example could be that, say you want to check, say take 4 and 5. So something which is this one, which we can calculate. Take 4 and 3, 4 balls, no, 3 balls and 4 boxes. Take 3 balls and 4 boxes. So it can never be on 2. So 3 balls, 4 boxes means 4 to the power cube minus, that is this one, 4 to the power cube. So I have taken this 3 balls and 4 boxes. So 4 to the power 3 minus 4c1, then 3 to the power 3 plus 4c2, 4c2, 2 to the power 3 minus 4c3, 1 cube. Calculate it. Tell me what is the answer you're getting. Some of you can verify and tell me quickly. We expect to get 0. So are you getting 0? Some of you?
Yes, sir.
Yes,
Yes, sir.
it should not take you long. Good. So 0. This is 0 will get. See, it is amazing that you just calculate something. So that's why in some books they will write that number of onto functions is f of mn, and they will write here that m greater than equal to n. But is not required, because if m less than n, the answer should be 0, and this formula gives you that also. So no need to write f greater than equal to n. Similarly here also, the other thing also same thing. One function also I told you that it was n choose m factorial m. No need to write that n less than equal to m. Of course, if this is this, that not this one. So let me just write first. Here for onto function, if you want, so I'm saying that number of balls must be greater than number of boxes, if, or at least equal to, if you want onto function non-zero. So it means sometimes we will write m greater than equal to n. Otherwise there is no onto function. So m less than answer is 0. But I'm saying that this expression handles both of them. So for writing this, I need not make cases. Again, here, so this m greater than equal to n, and you understand this comment. Similarly here, for 1 function, the number of 1 functions was the number of 1 functions from m to n. Again, set f a to be 1 to 1 on margins I'm doing. That was n choose m factorial m. Now you know that if this is m and this is n, so we know that if number of balls, this is number of balls. Now number of this is more, number of balls is more and boxes less, 3 boxes and 8 balls. Then you know that it can never be 1-1. Somebody will have to share. Some balls have to go to the same box. And so you want that there should be at least as many boxes as balls are there. So it means now you want that number of boxes n greater than equal to m. You want n greater than equal to m for 1 function. But this handles both of them. If n less than m, then by definition we know that n choose m is 0, because you cannot choose anything out of it. Means suppose n is 4, suppose n is 4 and m is 11, you cannot choose 11 out of 4. So this anyway is 0. It is in the definition only incorporated. And so if we can say that it is true for both. So I need not write also. All I know is that for n less than m, I know value is 0. Here it is evident because one step n choose m is seen to be 0. Here it is not so evident. You have to calculate and then find that, oh, really interesting, it is 0. It should be 0. Okay. So this can be given alternately, that somebody can ask you that, okay, find this value or some other value, this kind of value. Then you know factorial 5, this kind of value. Okay. So fmn is the expression. I will introduce one more expression now. That expression is smn. Smn is number of ways to put m balls. First, always balls come. M balls. So I will have to write distinct also. So m distinct balls, mind you, into n identical boxes, not distinct, n identical boxes. No empty box allowed. No empty boxes allowed. So it is not onto function, that you understand, because identical thing has come, so onto us cannot be. But this value has a relation with something. So let me go back and this. So n boxes here also I must write as a word of caution that this also is same thing, that ways to put m distinct balls into n distinct boxes and comma. It will be no empty boxes allowed. No empty boxes allowed. Onto functions, we know very, very important formula. If you when you go and when you do say IT, some electrical, computer science, or other physics, or except mechanical, chemical, okay, first semester or something, okay, then this of course will be lifelong. You have to use it, this kind of thing, reasoning, discrete mathematics. It's the heart of computer science or electrical, electronics, or any other thing. Okay, so here if nothing is, no empty box is allowed, then you are getting this number as FMN. That we know FMN how to calculate. That we have given you expression only, derived also. Now SMN is number of ways of to put m distinct balls into n identical boxes. So of course this will be, this we know the value now, this will be FMN upon n factorial. This we can derive quickly, one line. Why? Because see, this is say 5 balls, same thing, 5 balls and 3, so 5 different balls and 3 identical boxes. One is this, and one is 5 different balls and 3 distinct boxes. So this number only is S53, and this number only is F53, because the way we have defined these numbers. Actually S53 is not without its own charm. Actually it's called a Stirling number of second kind, but you don't have to read it. I'm just telling without telling the name. So S53 is this one. Now it is used in literature, S53. Now what is this to this? See, if suppose here balls are distinct, B, B, B. You are arranging these 5 balls. Say you have got red, green, blue. I told you study also something, red, green, blue, and say white and turquoise. Some 5 balls you are arranging. Any distribution, ball not empty, no box is empty. Any distribution like this. Now the moment you change levels on the boxes, then each such distribution, mind my words, watch out, each such distribution will lead to 6 distributions, factorial 3, because I can put the labels, this same RG, the BWT, I can put in B1, B2, B3, B2, B3, B1, B3, B1, like so 6 possible ways, because these all are distinct. These all are inside distinct things are there. So it means I'm saying that each way of putting balls into boxes, in identical boxes, each way of putting these distinct balls into identical boxes, the moment boxes are leveled, each will give rise to factorial 3 distribution. Factorial 3 means number of grouping, number of boxes. So it will give factorial 3, not 5, factorial 3. So it means from this to this, you are saying that root is that calculate S53. For each of them, multiply factorial 3, you should end up with F53. Same reasoning holds for the normal case n. So it is, your answer is this, is 5. If you remember, we got this answer as 25, yesterday, 25, identical. And this answer we got was 150. So 150. 25 I did another way also, 25. 25 directly also I can get, but because numbers is small. Say for example, I can write here that I did yesterday 2, 2, 1, maybe 5, and then 1, 1, 3. Because identical boxes, I don't care which has 2, which has 1. I just write. So this 2, 2, 1 case was factorial 5 by factorial 2, factorial 2, factorial 1 into 1 by factorial 2. That was because it is boxes are identical. This one, so this one. So that number was 120, and upon this is like 8. So this is 25. 120 by 8 is 15. Sorry, 15. And this number is factorial 5 by factorial 1, factorial 1, factorial 3, and times 1 by factorial 2. So that is 5 choose 2, that is 10. So 10 plus 5, 25. But you cannot do the same thing for bigger numbers like 8 balls, 10 balls, 12 balls. But my formula will take care of it. Suppose 12 balls and 3 boxes. I can use this. Maybe calculation will be a little lengthy, but the expression will be there. Computers can do it, or even it is 8, I can do quickly for 8. So this is this one. Okay. One more thing that is very interesting is this one. About F only. I should have written here that. So about F, one more interesting thing is this, that if you have got Fn2, Fm2, suppose Fm2, I'll write here, Fm2 will be 2 to the power m minus 2. That's very good looking result, Fm2. Why it comes like this? First, you can derive from here only Fm2 right here. So this is m2 to 2 to the power m, and minus 2 c1, one step it will come. What it tells you that, see this way, that if there are m balls and 2 boxes, the only way that some box is empty is when either all of them go to one box A or box B. And so there are only two functions in which two functions means every ball, all balls go into one box, that's one, and all box go in other box, that is box 2. And you know that there are 2 to the power m total functions because n to the power m, every ball could go in two ways, so 2 to the power m and minus 2. So this is good looking f2 m2. So number of onto functions A from a set having 4 elements to set having 2 elements is just 16, 2 to the power 4 minus 2. So this kind of thing is there. If 2 is there, easy number 2. 3 also I will tell you, R3 another thing. Okay. So this wraps up about this one. Now let me, it's time that I will make some results, and then I'm trying to make a column so that you will understand what we have done till now. So this summarizes many things. So this is, I'm saying balls or ball type, box type, ball type, box type, and here empty boxes allowed or not, that this question will be answered. So this is 1A result. For my 1A result is ball type distinct D, box type distinct D and D. This is yes, empty boxes allowed, no. So it is yes, it is no. This is, I will write 1A, 1B. Formula. What is the expression that you learned? So this formula was an R balls. So R balls into N boxes. R balls into N boxes. Like that I'm saying R balls into N boxes. Now, and then the assumptions are that we very much understand that any box can hold any number of balls. Means some box can hold 10 balls, 18 balls, whatever you like. So each box is large enough to hold any number of balls. That is one. And second thing is that order inside the boxes is not significant. It's not like rings and fingers. Means how you arrange, suppose there are 10 balls in a box, how you arrange, that does not matter here. That's the assumption. So according to that, we are answering the questions. They will be given also. This is this. And so this formula is just R to the power N. It's just number of functions. It is number of functions, total functions, these functions. 1B, ball type again same, distinct. Empty box allowed? No. It means all no box allowed. It means it is onto function. This answer is big answer. That is FRN, which we have told you what it is, FRN. Of course, you know that FRN will become 0 if you have got number of boxes less than number of boxes more than number of balls. So it will of course be 0. So FRN. Okay, in general FRN. Now second case will be, so this is called function, this is called surjection. Surjection, you know, surjection or surjective function or onto. Second A, this case will be distinct. This will be distinct and identical now. Distinct, identical. This one. Empty box allowed? Yes. Empty box is allowed? No. So this is 2A, 2B. Now, why I'm writing this 2A, 2B? 2B will come from 1B directly. 2B. So 2B comes directly. 2B is just FRN upon N factorial. That only I named as SRN. This was not SRN. So this is just this one. FRN by N factorial. Because I told you that each distribution here, remember the N boxes. So each distribution identical case, the moment you change the level, you can multiply by N factorial. So this entry times N factorial is this entry. But I know FRN because formula is there. So I will divide this to get this one. So for example, I got 150 here. Remember 5-3 case, 5-3 case. So this case 5-3 case, R is 5, N is 3 case. We got this number to be 3 to the power 5, 243. This number was 150. And from this number, I got 150 by factorial 3. That is 25 from this number, 25. And how I got this number? This number was 41, 5 distance. This number was 41. So this number I got by, see, now empty box is allowed. So now we are making it empty box allowed means now you are saying that, okay, it means I can use either 3 boxes or 2 boxes or 1 box. So if you use all the 3 boxes, then answer will be FRN. It will be of course more than 150, right? This 150 will of course be counted. Sorry, this 25 will of course be counted here also. So it is FRN by N factorial plus, so all boxes used, or FRN minus 1 by N minus factorial, all the way till f r1 by 1 factorial. Means you are using all the boxes, n boxes, then n minus 1, then 1 for here. So this calculation was this one, that if five distinct balls and 3 identical boxes, this answer would be f5 3 over factorial 3, boxes used 2, f5, boxes used 3, boxes used 2, and boxes used just 1. So it will go till all the way. So now you know the answers. f5 3, already I did 125 by 6. f5 2, I told you 2 to the power 5 minus 2 over factorial 2. And f5 1, just 1. All will be 1 only, 1 by factorial 1. So 1 by factorial 1. So this is 25, and this 32 by 2, 16. No, this is 25 minus 2, no, 32 minus 2, 15 actually. So 32, this is 25 is all right. 25 plus 32 minus 2, that is 30 by 2, 15, and plus 1, that gives you 41. So here 25 means that in this you are saying that you are distributing all the 3 balls. Means it may be that 2 are here, 2 are here, 1 are here. In these arrangements are those kind of arrangements in which you have got, this is maybe 2 and 3, this is 0, like that. Again, which one I don't care, because all balls are identical. All boxes are identical, so I don't care which B. So nothing like choosing. It's just that how many boxes are being used. One box used, of course, only one box used, you will get just 5. This 5 is here or here or here, does not matter, because all boxes are identical. So remember, we know very easily number of ways of distributing distinct balls into distinct boxes. With empty boxes not allowed, that is onto function. And if I do the same problem, then that is one step. From no to no, it is one step. This no to no. But this, yes, this 2A case you won't get from 1A. Rather, 2A you will get from 1B, applying it for n balls, n boxes, n minus 1, and all the 2 1. So this is very important result. This result, you see how important this result is becoming now, FRN, because next answers are by this only. So we have dealt with this one, 5 distinct balls, this one in all varieties, 4 problems. Next, I will now go to other 3A, 3B. Any doubt here? Please read it 2-3 times in a study hour. Many people are not clear about it. I would say at least 80% people, they just do by some kind of experience. Okay, this kind of thing. Okay, now next I will do other things. Next will be this one. That next you have got 3A, 3B. I will call it 3A, 3B. Remains same. So this is again ball type. This is again ball type, box type. Then here empty boxes. Empty boxes allowed or not, this one. And then formula and this one. So expression formula, this one. So 3A here, I will take here identical, distinct. 3B will be identical. So I will write here like this. Identical, distinct, identical, distinct. Here empty boxes allowed, yes, no. Then 4A, 4B means 8 problems, 8 types. Identical, identical, yes. Here identical, identical, B problem, and here no. This one. Now this is again something here, that something you know already. The best part is that in all these tables, some part you know very easily. For example, this one you know. Ball type and box type. Ball type and box type is identical. It's just the integral solution. Number of ways of dividing 5 chocolates to 3 children. Children become boxes, distinct, and chocolates become balls, which are identical. So this we know already. This is integral solution. This answer is R plus n minus 1. Choose n minus 1. If you R balls, same R balls and n boxes. Now this is same as x1 plus x2 plus xn equal to R. Distributing R identical balls in R identical balls into n distinct boxes, or distributing R identical chocolates or R chocolates between n children, where anybody get any number of things. 0 allowed, S yes, empty boxes allowed, empty allowed, it means xi greater than or equal to 0. For this, if you do this means x1 plus x2 plus xn equal to r and xi greater than or equal to 1. At least 1. Empty not allowed. No, empty is no. Just like this one. So this answer this you can calculate from here only. That I will tell you the result. That will be coming just r minus 1, choose n minus 1. Because here it is one line. Here you want that everybody get at least 1. So it means n chocolates are lost. So you have got only r minus n. So r minus n plus n minus 1, choose n minus 1. N cancels. So r minus 1, choose n minus 1. That is number of non-negative integral solutions are this one. And number of positive integral solution means at least 1 is this one. So these two we know very easily. So this is not a problem. Actually, this has got also a name in literature. This is called compositions. So this is called just like something was called. So previously we called it function surjection. This is called sometime set partition. Set partition. Because we are partitioning the set. Set because you are saying that this is distinct, this is identical. So set partitioning means you are partitioning the balls into some kind of boxes. So set partition, as opposed to next term will be that here this will be called integer partition. This is called integer partition. Why? Because it is just like, say, suppose you want 5 identical balls. For this there is just notation 1. I will write no. So this is this notation is PNR. PNR, where PNR is called number of partition of n into r parts. Number of partition into r parts. That means that if you take P53, so or number of ways of writing, or it is same as number of ways to write n as a sum of r positive integers, not non-negative, because r parts you want r positive integers. For example, 5, 3, case of 5, 3. So writing 5 as in 5 you're writing as a sum of 3 positive integers. So 5 you're writing 1 plus 1 plus 2. This you can write 1 plus 1 plus 3, or you can write 1 plus 1 plus 2 plus 2. This one. Order does not matter. Order does not matter because you are just partitioning. So order see, it is box identical. Sorry, box identical and box also identical. It means these are identical things and box is identical. So only thing matters is number, nothing else. Only thing matters is numbered. If it is set, then
What PNR?
What is P? What you're saying?
PNR, what is it?
Sorry, it is PRN, not PNR. PRN. That I'm telling you, just PRN is just name for it. How to calculate that I have not told you. PRN is number of ways to write. This I have to change. 1 minute. Write R into n parts. Just as I gave you the name SRN, if you remember SRN. Similarly, I'm saying that PRN is the number of ways to write R, positive integer R, as a sum of n positive integers. For example, 5, you want to write 5 as a sum of 3 positive integers. So how will you write 1 plus 1 plus 3 or 1 plus 2 plus 2? No other way. Are you getting my idea? So this is actually the thing. This only is thing. If you want this one, this is this only. But how to calculate PRN? Just like FRN, that we have not told you. Actually, there is no formula for PRN. You will have to, it's just name is there. You will have to find PRN by other methods that I will do. So just call PRN. Means PRN, SRN, there is some formula SRN because we found FRN, and from FRN, SRN came. No, SRN was SRN was this one. SMN is this one, FMN. So formula was there at least. But now there is no formula for this one, partition. There is some recurrence relation that we will use later to calculate. So just now use it as a symbol that I'm denoting this number of ways by this one, PRN. Okay, this is PRN. So number of partitions of R into n parts. So this is PRN. Now what will happen here? That And what about this one? That empty box is allowed. Yes, here only 3 boxes are there, so 3 parts compulsory. You cannot, if you write 5 equal to 1 plus 4, that's not allowed because it has got only 2 parts. You want 3 parts, n parts. So you're saying writing number of ways of writing r as a sum of n positive integers, n positive. So number of ways of writing 5 means number 5 you are writing integer 5 as a sum of 3 positive integers. So 1, 1, 3. 0 also you cannot take positive integer. If you take 0, then it is it is the 2 parts only, not 3 parts. So n parts. So this is, and this answer will be, this is just like sigma. This answer is that now you want 5 to write still, but empty allowed. So you can also write 5 equal to 1 plus 4 and 5 equal to 5 is allowed. So you will write here that this answer will be PRN n parts plus PRN minus 1 parts till PR1. So you can go till here. Means it is sigma PRI, it is sigma PRI and I equal to 1 to n. Means you can write in any way you want. For example, 5. For 5, you can have 5 is 1 plus 1 plus 3, 3 parts. 1 plus 2 plus 2. This corresponds to the case that no box is empty. No box is empty because all 3 are used. Or you can, so this is answer for this one, PR3. Now you can also write this as more parts. So suppose you write, suppose you can write not more because there are only 3 balls. So less you can write. So you can write 1 plus 4, that is 5. Or you can write 2 plus 3. No need of 3 plus 2 because all balls are identical. So 2, 3 is same. 2 plus 3. Okay. 1 plus 4, 2 plus 3. Nothing you can write now because 3 plus 2 is same. So it is not an order. Okay. 0 plus 5 you cannot write because this is not. Then only 1 is this one. So 5 has got these partitions. 5 integer 5. That's why it is called integer partition. Integer 5 is partitioned into three parts. Here 2 parts. So 3-part partition, 3 parts. Here 2 parts. Here 1 part. So if you want that number of ways to distribute 5 identical balls, so only number matters. Ball type no. So 5 identical balls into 3 identical boxes, such that no box is empty. It means you are dividing 5. You are writing 5 as a sum of 3 positive integers, whose sum is 5. And then if it is empty boxes allowed, 1 or more boxes can be empty. Yes. Then you are saying that you can either you can put all balls in 1 box, or you can use 2 boxes or 3 boxes. So 1, 2, 3, 4, 5. This will be the answer for this one. 1, 2, 3, 4, 5. So this kind of thing is there. This is easy to calculate. This is not a problem. But for 3 cases, so I will take bigger number. Otherwise, it will be a problem. So this answer, see, this answer is trivial here. Trivial. So this answer is trivial for the case of this one. So I'll write somewhere so that you remember. So I'll write for this case, 5-3 case. So for 5-3 case, this answer is this answer. This answer, if is not allowed, is just 2. Means the number of ways to put 5 identical balls into 3 identical boxes. No box empty. Empty box is not allowed. That is just 2. These 2. And number of ways to put 5 identical boxes, 5 identical balls into 3 identical boxes where box can be empty. Then answer is 2 and then 1, and so this answer is 5 total. Just check, because you can write as 3, 2, 5. No, 2. This is 2 part. This is 2, 2, 4, 1, 5. So 5 ways. So this answer is then 5 ways. This answer is your, when empty box allowed is 5. So it's a very small number. So here what I will do to draw, I will make this number bigger. I will write now. I will make one case in which, say, 12 identical balls. I'll take 12 and then see that how we can do the work. So 12 and 3 case I will deal with. Any doubt here? Okay, many things you know. For example, this you know. Now I will derive from here only this one. See, 4a will come from 3a and 4b will come from 3b. I write here that 4a will come from 3a and 4b will come from 3b. Because 3a, 3b we know, so I will change the levels and I will understand that what is happening. So let's do our next problem. Then ball box will be closed. One more remark I will make just after that. So now we are doing a big problem. 12 identical balls. 12 identical balls. 3 identical boxes. Box I will keep 3 only because for lot of trouble will there. 3 identical boxes such that no box is empty. Such that no box is empty. And one is that empty boxes allowed. So one question is this. Other same question. Empty boxes. Same question. Empty boxes allowed. So distribute 12 identical balls into 3 distinct boxes. What are they? Such that empty, no box is empty, here empty box is allowed. Okay, so it means this is this for this question. For this one, A and B, suppose, or not A and B because A I have given this one. So empty box is allowed. I have given A, so I will write this as A, and this as B problem like that. Because I have followed the same notation here, A and B. A I have followed from empty allowed, B not empty. So as I promised you, it will come from here. So you want for first, let me do example of B. B example first, B. So empty box allowed. No, A is not allowed. A, I will do A first. Empty box is allowed, A. So you want this time, you want, understand carefully, you want here. Now question is that 12 identical balls, 12 identical balls, and three identical boxes. You want number of ways. Okay, but you know 12 identical balls and 3 distinct boxes. This answer you know. This and no boxes, no box empty, no box, no sorry, empty allowed, empty allowed. Here also empty allowed. Empty allowed. So I will from here I will come to here. Though this answer I know. This answer is x1 plus x2 plus x3 distinct case. This distinct case. This distinct case. This is 12. This answer I know is integral solution. 12 plus 3 minus 1. Choose 3 minus 1. That is 14. Choose 2. That is 14. 13 by 2. That is 91. This I know 91. Okay. This I do not know. This I want to know. So I will evolve this method. I'll write that. Okay, let's look at distribution type. This is right B because three boxes are identical. So I will write B and B. Now distribution type. Because balls are identical, so the only thing matters is that how many balls are there in each box. Which ones does not matter because they're identical. So how many? So it can be distribution type can be ABC, means all boxes have distinct number of balls. All boxes have distinct number of balls. Maybe some 0 also, but distinct number of balls. Then here, distribution type can be AAB. AAB means two boxes have equal number of balls. One has different. A is not B. Here on these cases, the different letters. This is different. So this one, and third type is AAA. This one. It means either all boxes will have unequal number of balls, or two boxes will have equal number of balls, one box different, or all 3 equal. This case is certainly 4 because 12 balls are there. If 13 balls is there, then this case will not occur. In this case will occur only when number of balls is a multiple of 3. So 4. Let's ABC. Let's write some part of ABC. So ABC contains this kind of thing, that 3, 5, 4 distinct number, or 1, 11, 0 allowed because the empty box is allowed. So this kind of questions comes here. ABC that I will not count. I will call it K. I will call these numbers K. That there are K distributions. AAB I will count by hand. AAB. That is A can start from 0. So 0, 0 and 12. And A can go to 6, 6 and 0. So total 7 cases. Total 7 cases, but you understand that here somewhere 4 will come, which will not be counted here because A is not B. Here it is A is not, B is not C. Here again A is not B. Here only one thing is there, nothing to worry. So 4 will not count. So 0 to 6, 7 cases are there. So this is only 6 cases. Now here, this is just one case, 4. Now, the moment, suppose you have distributed it. Now, big question is this. The moment I change levels on the boxes, B1, B2, B3, level changed, then this same distribution, this for example 3, 5, 4, this leads to how many distributions? That is the question. Because this answer I know. This column I know the answer, and so I'm asking this one myself. So I will call it, let's say, multiplying factor. Multiplying factor. What happens that from here to here, multiplying factor is factorial 3, because all box have got different number of things, different number. So see 3, 5, 4, this one, and then distinct number here. Here it is B right now. The moment you change the level B1, B2, B3, then it has 6 ways: B1, B2, B3, B1, B3, B2, and all those numbers. So here you will say that one box got 3, one box got 5, one box got 4. But here you will say box 1 got 3 now. Here box 2, here box 2 got 3. So it means they are different. So it means each such will to factorial 6. Each such will into factorial factorial 3 hybrid and factorial 3. Each this kind of thing identical will give rise to only 3. Only 3, because you have got, suppose you've got 3, 3, 6, this kind of ball, 3, 3, 6. So the moment you write levels on it, you can write B1, B2, B3. Then you can write B1, B3, B2, and then you can write, so this is still bigger. No, all right. So you can write here 3 only, because B1, B2, B3, this is B1, B2, B3, and 1 again will come. So it means that only 3 ways, because 2 are identical. So 3 ways. So this number become 18. This number becomes 6k. This is 1 is just into 1 only. This number becomes 1. So total becomes 6k plus 19. And what I want this one. I want only identical way. So I want this one. So I want these numbers. I want sum of k plus 7. But k I don't know. But because I know this column, so I can calculate k, because this answer is of course this answer is 91. So 6k plus 19 is 91. So k equal to 72 by 6. So k is 12. And so your answer for this will be 12 plus 7 equal to 19. So you have got 19 ways. You have got 19 ways to put 12 identical boxes to identical boxes. Answer is coming again from chocolate and children. So you are just devising that how these things changes. Once I change the levels on the boxes, then one such distribution with unleveled box will give rise to, in one case 6 distribution, in one case 3, in one case only 1. So these all have got different multiplying factor, but end result I know 60 plus 19, that answer I know 91. So I calculate k and this one. Here one word of caution: suppose you make a mistake here, 4, 4, 4, you count here of 7, then no problem, you will get k to be something which is not integer. So you can get that you must run some mistake. So problem will of course tell you this also, warning is inbuilt. So not getting integer means some mistake you have committed, you check earlier. Okay, so this is one. Similarly, let me do the problem of, this is same, exactly same. 12 identical balls, 3 identical boxes, no empty box allowed, no box allowed. So B. So B problem will come from corresponding problem of distinct boxes. So this I will write now. So next will be that if it is x1 plus x2 plus x3 equal to 12, and you want now empty box is not allowed, so this is the case. Empty box is not allowed. A part solution. A part or B part? B part. So solution of B part is like this. So this is 1. So 1 is gone, 3 is gone, 9 remaining. So 9 plus 3 minus 1, choose 3 minus 1. 11, choose 2, that is 55. Okay, now I want 5 different balls, 5 identical balls and 3 identical boxes, again identical boxes. So distribution type is ABC, distribution type is ABC, AAB and AAA, again same type. Now I want that it must not be empty, and no box should be empty. So only so 3, 4, 5 type will come, 0 will not come, anything. So this number will be k. Here 0 cannot come, so 1, 1 and 10 will come, 1, 1, and then 6, 0 cannot come, so 5, 5, 2 will come. So 1, 1, 10, 2, and then 5, this will come. Okay. Now this arrangement I will count. This you have to count, hand count. So that is just 4 ways. Why? Because 4, 4, 4, will be crossed out. So this is 4 ways. Okay, this is 4 ways. This is your k ways. This I don't have to count, k ways. And here multiplying factor. Once you change the level of the boxes, B1, B2, levels of the boxes change now. So now that will happen k times factorial 3. So 6k. Then here, this one, this is 4 only. So 4 times 3, that is 12. And this is 4, 4, 4, 1. And this is into 1 only. So this is 1. So 6k plus 13. And this number is known to be 55. So 6k plus 13. So 6k plus 13 is 55. So 6k is 42. So k is 7. K is 7. And what you need just this one. You need this sum. You need this sum. So this sum is k plus 5. So 7 plus 5, that answer is 12. So you've got 12 ways to distribute that one, identical balls in this one. So the number of ways to distribute 5 identical, no, not 5. Okay, 5 only. 5 identical balls into 3 identical boxes such that no box is empty. That number happens to be then 12. This number was 19. So like that, you can have this thing. One case remains that you already have done. So I will just remark that. So this 2 problem also you try later. Again, yes.
Sir.
Yes, tell.
In AAB case, 5 cases, sir.
5? How 5? 1 to 5 only, no?
1, 2, 3, 4, and 5.
No, 4 is 4, 4, 4.
Sorry.
4 is equal number, right? So this will not come, and 6, 6, 0 also will not come here because 0 not all boxes used, correct?
Yes.
Anyway, suppose you
Okay.
make mistake. No, you make mistake. There is a good thing here that k will be not integer. So you will be forced to think again that something you have counted wrongly. This method works very well even if I increase the number of balls, 100 balls, 200 balls, because this I can quickly calculate. And if I do a problem also, big problem I will do also one in which balls will be large enough. Really, it's a good method. So you can find this in this is. So just master this. If you master these 8 things, then everything is done. You'd have a very clear reasoning. All of you, please take effort. You will have reasoning. I have taught this chapter at least 30, 40 times, okay, to international students also. So this is really interesting chapter. Okay, now next let me go through one more case that I have discussed, but then here I have to again tell that because we are assembling every result, we are gathering all the results here. So in all of them the assumptions were that box ball type of assumption was written only. Other thing was that any box can contain any number of balls, and significantly we never talked about arrangement inside the boxes. Means in all of them we have assumed, or it will be told also, unless given otherwise, that the arrangement inside the box arrangement of the balls inside the box does not matter. It's not that 5 balls are kept here, but there is one situation where it will be told that no, arrangement matters, and then answer will change, which I'm telling you now, which is not covered here. So that example was we did in rings and fingers, we called it, because that was more natural thing to tell, rings and fingers, because there we understand that okay, this will matter. So this in balls and box language I will say that answer of m distinct balls into, sorry, r only, I'm writing r, so r only, r distinct balls into n distinct boxes, number of ways. So number of ways to put r distinct balls into n distinct boxes. Any box having any number of things, having any number of balls, any box, and then order of balls inside boxes is significant or matters. I mean, this to be taken into account, significant. This is, so that was rings and fingers. That was your rings and fingers example that I did. So this answer was that r balls and n boxes. Then this answer was let me derive. This answer was, I think, r plus n minus 1, choose n. Here, this one, I have said empty boxes allowed here. Not allowed also same way will come. Here I'm saying empty boxes allowed. So r plus n minus 1, choose n minus 1, and times factorial r. This was the answer. This also can be simplified as I think, this is n minus 1 rather, n minus 1. Okay, so let me check now how you can simplify. So this derivation was like this way. If you remember that we did for 4 fingers of a hand, 4 fingers and 5 rings. If you remember, I told you diamond, sapphire, no, ruby, topaz, no, all 5 rings were there. So your first thing was to decide that how many rings you want to wear on all 4 fingers, 1 finger not used. So here you want 1 ring or 2 rings or something. That was x1 plus x2 plus x3 plus x4. That is x1 on the ring finger 1, finger 2, finger 3, finger 4. So that was 5. So first you forget about this one. First you just decide how many numbers you want on each ring, on each finger. So that number is, so this solution, this is the number of integral solution. So that answer was 5 plus 4 minus 1, choose 4 minus 1. That is 8, choose 3. This one, if you are allowing some fingers to go empty also, that was written in the problem, that it is not necessary that each finger has a ring. Sometimes they give you, it is necessary that each finger must have a ring. Like, okay, something that rings and fingers, so that the girl wants that every finger, no finger should look barren, and so she wants that every finger should have at least 1 ring or at least 2 rings. Then of course we can modify this. This easily modifies. So no new case I'm making. So so this is 5. So this is the way of arranging. So say this some number. Say one arrangement will be, suppose this you have decided that here 2 rings, here 2 rings, here 1 ring, here 1 ring, like that you decide 2, 1, 3, 1, 4, or here like that you decide. So these cases, it's 3 cases. Many cases are there. These are all cases. Now in any one of them, now once you have done this, your job is that you've got 5 rings. Now these are the places for rings. So you have got diamond, topaz, then ruby, emerald, gold. So now this is D, T, R, E, G. You just have to arrange on the symbol. Means that is factorial 5 ways, because you can write D, T, R, anything you can write. So you will get that one. So you just have to arrange them, nothing else. So same thing here happens. So let me, so this is 8, choose, so this answer would be 8, choose 3, and times now 5 rings, because so factorial 5, that is your answer. This also can be simplified and written like this: factorial 8 by factorial 3, factorial 5, factorial 5. So understand this answer will be, this cancels. This answer is then 8, 7, 6, 8, 7, 6, 5, 4. So which I will write as 4, 5, 7, 4, 5, 6, 7, 8. And I will say that how I can reduce, how I can get this expression another reasoning, another way. That also I will get another reasoning. So let me simplify this also. This also I will simplify like this. So this simplification will look like this final answer or simplification. So this is also equal to, let me simplify this. So this becomes, I will simplify here, say, so here simplify. So r plus n minus 1 factorial, and over n minus 1 factorial, r factorial, this all cancels. This one. So what you are doing is that you are writing here. So you will start from, you are starting from this one, n. So you're starting from n. So this is n plus 1 till r plus n minus 1. This is your answer. This answer also is n plus 1 all the way till r plus n minus 1. This one, or n plus r minus 1 you write if you want. So you write n plus r minus 1 if you want. So n plus 1 like that, n plus r minus 1. This is also one answer, which is this one. Here n equal to, here 4 rings and 5 fingers. So n is your, n should be 5 rings and 4 fingers. So n is 4. Here n is 4. 5 rings. You are distributing 5 rings into 4 fingers. So n is 4. So 4, 5, 6, 7, 8. Because 4 into 4 plus 5 minus 1. Now, why this is so simple to derive in another way also, that I will tell you. So it is n plus r minus 1. Now say same example here. Say first ring has got how many choices? First ring has got 4 choices. It could go to either finger 1, finger 2, finger 3, finger 4. So let it go to any finger, say finger 2. Okay, finger 2. The moment you have got here, then for second ring you have got how many choices? That is now 5. Because why 5? That it can go on this new fingers, these fingers, or here it can go up or down, this one, below or above. So 5. So the moment first ring has 4 fingers, but wherever the first ring has 4 choices, the moment first ring goes anywhere, then it creates 2 places, one up, one down, and other also. So you have got here 5 choices. So 4 into 5. Now say second finger, second finger has 5 choices. Suppose second ring has 5 choices. Second ring is taken place. So suppose second ring goes here, second ring goes here, second ring goes here, second ring here. Then now you see, this you forget now. Second is gone here. So again you have choices 1, 2, 3, and second first thing. So 3, 4, 5, and 6. So 6 choices. So choice increase by 1 step each time. So that is why first ring, second ring, third ring, rth ring. This is first ring n, second ring n plus 1, rth ring n plus, first ring is n plus 0. Say n plus 1, n plus r minus 1. So that is why you are getting this kind of thing. So this is one good way of arriving, or exam quickly you can write 4, 5, 6, 7, 8 like that. Which does not apparent in this justification. This is just true integral solution. This is entirely different justification, which of course holds. If empty you allowed, if empty you don't allow, then you don't do by this method, then this method only. If empty rings are allowed, if empty fingers are allowed, then this method is workable. This one, otherwise general method is this only, integral solution, and then multiply just this one, this kind of thing. So answer is same for both cases, but I'm saying that you cannot derive this easily from that case. But this is of course all time. So this you know already. So it means you also did one case, only one case in which rings and fingers, in which you have found that it matters. It matters here. Okay, let me check what else I can do. Oh, I have to do something more also. So let me do fast 1-2 more things. Okay, any question on this one? One is this derangement. Now words, anytime when you read a word, you see a word you do not know, you should open up dictionary, preferably Oxford Advanced Learner, and then check the meaning. It will be good for you. Language is our power. So this derangement. So derangement means that something is not in the right place. So many educators, teachers, they write derangement. That's simply illiterate. There is no word like derangement. Okay, so it is derangement. See, derange also means deranged. No, if you say that somebody is deranged, means he has gone mad, he has gone out of track. Somebody is deranged. Okay, so derangement means that nothing in the right place, no permutation. The classic problem is this, that suppose you have got n letters, L1, L2, Ln, n letters. So this is letters, n envelopes, n letters, and you have got corresponding envelopes, E1, E2, En. So take the case of 2 or 3. Now the question is that how many ways it can happen. So number of ways such that no letter is in the correct envelope. Correct envelope. No letter. Imagine a case that suppose from your institute, from your campus, you select 10 students, and about 10 students marks, they are making a report and they are sending to the parents. So in how many ways it can happen that none of the 10 parents get the reports of their own child, they get someone else's child, like L1 gets E2 child, those kind of things. So same here, means L1, L2, Ln, and E1, E2, E1. So in how many ways it can happen that L1 does not go to E1, L2 does not go to E2, and L does not go to En. This is abstract thing. So it means nothing in the right place, nothing in the place it is supposed to be. So it is called derangement on n symbols. So it is called Dn. So Dn is called derangement. Notation is always a like weapon of mathematician. Derangement of n symbols. This n so that has got some expression also. Dn has got a nice formula coming through pi. So Dn is factorial n, 1 minus 1 by factorial n, 1 by factorial 2 minus 1 by factorial 3 plus minus 1 to the power n 1 by factorial n. So this kind of answer you will get here. This one. So this is your expression for this kind of thing, that okay, this is ultimately you are getting this one. I will derive it now shortly. So first understand this dn. So it means understand this one d1. D1 means what? D1 means one letter and one envelope. So nothing derangement. If there is just one letter and one envelope, then there is no way it can go wrong. It has to be default by true. So d1 equals 0. There is nothing. D2. If you have two letters and two envelopes, then only one way you can go wrong, when L1 goes to E2 and L2 goes to E1. So D2 is 1. D3, 3 letters and 3 envelopes. Things get interesting now. L1, L2, L3. Now, L1 cannot go to E1, so L1 can go to E2 or L1 can go to E3. If L1 goes to E2, then L2 can go to E1 or E3, but then L3 of course must go to should not go to E3. So L3 can go only to E1, and this will be then, no, L3 can go to E2, and this is then E1. No, E2 is already taken, man. So let me write again this. So L1 goes to E1, L1 goes to E2. So E1 and E3 remaining. So now L2 will go to E3 and L3 will go to E1 because L3 cannot go to E3. Similarly, this could have been E3. So if E3 is there, then L2 will go to E1 and L3 will go to E2. So they are just 2. So D3 is 2. It so turns out that now higher numbers you cannot calculate just by case work. You can't. Try later. I'll tell you this one. So D4 is 9. See, 9 suddenly jumps. D5, what do you guess? Is 44. D6, 265. It goes like exponentially. D6, D7 will keep on increasing, 4 digit. So the number of derangements grows very fast. See, this is kind of exponential series. You understand also e to the power. It resembles that series e to the power minus x. Of course, it stops somewhere, but e to the power x series goes on and on. It never stops. It goes to infinity. But this stops. So this is this one. D6. So number of ways in which this is there. 6 symbol can be deranged D6. Like in scenario, imagine this one, that 6 people went to a party. At the counter, they all checked their umbrellas. Suppose, or hat. So suppose umbrella. They all checked their umbrellas. While returning, they all returned their umbrellas. In how many ways it can happen that nobody got his own umbrella back? That is again factorial 6. That is again D6 ways. That is D6 ways it can happen that nobody gets its back. Now I will derive it. Using something called pi that we already know. Pi is the beautiful thing. And formula tells you it is alternating sum. Because it is alternating sum, it is. So anybody who sees for the first time and you try to derive, he will try that alternating sum is there. So maybe it's a good work for it's a good work for those kind of things, for pi. Sum. So pi is like on our mind now. So we define like this. So we go to next page and I define this way, that let S be the number of ways, or set of S be the S is the like S is the set S is the number of ways in which n letters can be put into n envelopes, random, right? So this is n factorial, means without restriction, n letters, n envelopes, n factorial ways. Now we don't want something in this, so I will define set A1 as that A1 is the set of ways or number of ways. A1 is ways in which L1 goes to E1. I don't want, but L1 goes to E1. L1 goes to E1. A2 means letter 2 goes to E2. Similarly, A3, letter 3 goes to E3. And last is AN, that is letter N goes to EN, LN. So AN. Now I ask you this thing, that okay, but we don't want this. We want that number of those ways, in which A1 does not happen, because L1, we want L1 does not go to E1, but we negated it because it is easy for me to calculate L1 goes to E1. If L1 does not go to E1, there are so many choices, but L1 does not go to E1, so L1 goes to E1, I'm happy. Okay, it goes to E1, so L1 is fixed now. So this number is, this is now, so what I have to find in terms of these defined sets, that's the important thing, that you have to find A1 prime intersection A2 prime intersection AN prime, means L1 does not go to E1, and L2 does not go to E2, and Ln does not go to En, means no letter goes to its correct place. That is what this is, intersection is there. Now this you have to find. I have to find this only, this number of ways, this I have to find. Now you know from set theory that A1 prime intersection A2 prime, this we have done 2-3 times. An prime is total functions mod S, continuity of a size of S, minus A1 union A2 union An, cardinality of n, this one. And this is already n factorial, I know, and this I will calculate. This is A1 union A2 union An. That is by set theory we know that A1 or pi, this A1 A2 till An minus A1 A2 intersection means minus A1 A3 minus An minus 1 An. So intersection of, so this is first sum of all elements taken one at a time here, then taken two at a time, then taken three at a time. So it is twofold intersection of two at a time. So this is this one, then plus now threefold intersection A1 A2 3 intersection of set of three, all set of three possible intersections A1 A2 A4, like that. Writing is more painful rather than calculating is very easy. This one. Okay, so now this answer I know now. Now let's check this one. A1 means what? A1 means that L1 goes to E1. So this means that this A1 is easy. L1 goes to E1, okay, and L2, L3, and En, E2, En. I do not know how they go. This is just n-1 factorial. Mind you, we are not saying derangement. We are just saying, you are just committing that L1 goes to E1. What happens to L2? I do not know. It may also happen that L2 goes to E2. We are not concerned. So A1 mod, this one, A1 is E1. Similarly, A2 also is N1. That's the beauty of pi, that it helps you to focus only on one thing. You don't care what others are doing. I am doing my job. My formula will take care of that. Just like vectors, you give the directions, vector will give you the answer. You don't worry about that, how they cancelled, or you don't have to picturize or imagine that velocity must have been in this direction to produce this acceleration. You just use a machine, and the machine will give the output. So A3, so this all are this one, n-1 factorial. Of course, physical meaning is important, that I'm deriving also, and this is all n-1 factorial. Okay. So this tells you that this answer becomes this answer becomes, because there are n choose one term, so n choose one time n factorial, n-1 factorial. This is like that L1, in how many ways it can happen that L1 goes to E1, that is n-1 factorial, and there are n such things, L2 goes to E2, minus. In how A1 intersection A2 means in how many ways it can happen that L1 goes to E1 and L2 also goes to E2, means L1 goes to E1 and L2 also goes to E2, so gone. So only n-2 remaining, n-2 envelopes, so n-2 factorial. But how many such terms? N choose 2, because this intersection occurs n choose 2 times, all are equal values. Then plus n choose 3, n-3 factorial, and so on. So this number is, if I write n choose 1 as n factorial upon factorial 1 n-1 into n-1 factorial minus n factorial 2 times n-2 factorial n-2 factorial factorial n 3 factorial n-3 factorial minus 3 factorial, and so on. So this becomes that this things cancels, this cancels, this cancels. So we are getting n factorial upon 1 factorial minus n factorial upon 2 factorial plus n factorial upon 3 factorial and minus so on and so forth. So on and so forth it goes on. And if it goes on, then what will happen here, that this, I want this one now, I want this one. So this number will be this A1 prime, which I want A1 prime intersection A2 prime intersection An prime. That is n factorial minus, and this whole thing was n factorial upon 1 factorial minus n factorial 2 factorial plus n factorial upon 3 factorial, and so on and so forth. So n factorial is common, and I will write 1 minus 1 by n factorial. I will not cancel, just to preserve symmetry. I'm not cancelling 1 and 1. Plus 1 by 2 factorial minus 1 by 3 factorial plus, and you know that it is minus 1 to the power n 1 by n factorial. So this kind of thing. So this is the number of ways of arrangement of this putting the letters in envelope. So let me calculate D3 from here. D3. D4 may be good. D4 is 9. Answer is, so D4 is 4 factorial. Okay. 1 minus 1 by 1 factorial, 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. Stop, because you have to stop at n. So I'll calculate like this. So this is anyway 0 now. You will remember like this only, but final, of course, calculating you will cancel. So this is 4 by 2. So that is 4 into 3 here. This is 23 minus. This is 4 and this is 1. So 12, 1, 30 minus 4 is 9. Let's calculate D5. 5 factorial. 1 minus 1 by 1 factorial. 1 by 2 factorial. 3 factorial. 1 by 4 factorial. Minus 1 by 5 factorial. It will end here. So D5 is, we know it is expected 44. So this is 5 factorial here. 5 factorial minus, sorry, this is anyway not going to be true. This anyway is cancelled. So this I will not calculate only. The expression I am retaining just to have its beautiful symmetry. So factorial 5 by 2. So this is 5, 4, 3. This term is minus 5 times 4. This term is 5 minus 1. So that is 60 minus 20 plus 5 minus 1. So 65 minus 21, that is 44. So D5 44, D6, it will increase. Actually, it increases exponentially. So this is one thing that always asked. So this is called derangement on n symbols. Means number of ways in which you can have this one. Number of ways such that you have n different letters, and no letter goes in the correct envelope is this one. So this is one way of doing it. There is other way also called recurrence relation for it. That I will derive later, because I have not told you recursion. So that I will derive later recursion. That also is a different concept, recursive technique. Okay, so let me do just one problem based on it. That's not one or two. That's easy, not difficult. So one problem is this, that 6 person go to a birthday party, okay, and they leave their top coats. So they leave their top coats in the lounge. And pick them while returning. In how many ways? It can happen that first, exactly one person. It's very important to write these things. Exactly one. In combinatorics, exactly, at least you have to watch out. Exactly one person picks up his own top coat, his own, not someone else's, his own top coat. Exactly one. And second, exactly 2 persons. Exactly 2 persons pick up their own top coats. So these 2 examples. Then we can write something else also, at least 3. Okay. So I will write like this. See, this solution will be that exactly one person. So see, 6. Imagine 6 persons. So 6 persons are there: A1, A2, A3, A4, A5, A6. Okay. So there are 6 persons. Okay. Now these 6 persons are there. Now exactly one person picks up his own coat. Means out of 6, one lucky person. So that can change 6 choose 1. because you do not know which one exactly one. I just one number. So 6 choose one to pick that person. Call him A3. Suppose A3 is the person who gets his quote. So that job in 6 choose one ways. After that, there are 5 people. 5 people, and then these 5 people say remaining A1, A2, A4, A6. 3 is not there, and then quotes call it C1, C2, C4, C6. So now it is derangement because A1 does not get his own top quote. A1 does not get C1, A2 does not get C2, A4 does not get C4, A6 does not get C6. So means it is just then one more was there. So I think 5. So number of ways in which A1, A2, A5, A4, A6, none of the gentlemen get their own top quote back. That can happen in how many ways? That is D5, precisely that D5. No need to calculate. We already did our good work. So D5. So that's my answer, 6 C1 to D5. So 6 C1 and times D5 is 44. Just now we got D5 44. And so this will be 264. So this is 264 answer. This one. Second is easy again. Second, you are saying that exactly 2 persons pick their own top quote. So that's all this one. So that is 6 choose 2 because this time it can be A3 and A5 or any such combinations. So A3 A5 suppose get to visualize, consider one case A3 A5, and one of the cases A3 A5, then A1 remains, A2 remains, A4 remains, A6 remains, and their top quotes C1, C2, C4, C6. And now the question reduces to saying that A1 does not get his quote C1, A2 does not get, A4 does not get, A6 does not get. It means this derangement on 4 symbols can happen in D4 ways. D4, the symbol D4, and D4 value we know. So 6 choose 2 is 15. So 6 choose 2 is 15, and D4, of course, I told you is a 9. You can calculate, and this is 135. So this is 135 ways. This one. Similarly, suppose I say another question. If I add, and if I say that at least one person got their or picked up their own, at least one person got his own top quote back. At least, what is it? At least one person got his own top quote back. This one, at least one. Or fourth is at least 3. At least 3 people got. At least 3 people got. What is the difference? So for at least 3, it is better to calculate not. At least 3. At least 3 got. At least 1 got means you say total minus none got. Total minus none got. At least 1. At least 1 person got his own top quote back. So total number of ways minus nobody got his back. So this total means total is 6 factorial because 6 factorial ways can happen because 6 quotes and 6 persons we can give in factorial 6 away ways. Factorial 6 ways you can give away. And minus none got his own top quote back. So that is D6. So this answer is factorial 6. So that number is like 720. And then minus D6, and D6, I told you that D6 is calculated. D6 is 265. So this is 265. So you will get 5 and then 5 and then you will get 3. So you'll get 355. No, this will get 455. You will get 455. So this is the number of ways in which at least one person gets his own top quote back. So this is one. If it is at least 3%, then you can't do at least 3% means you will have to break into disjoint cases. That's the lesson I want to learn. That at least 3%. It means that you will say exactly 3 got, exactly 3 got, exactly 4 got, exactly 5 got, exactly 6 got. You can add or you can subtract total minus exactly 1, exactly 2. That also you can do. These things, this also you can do. So at least 3 got means here you will say this answer will be exactly 3 got. So 6 choose 3 and times 3 did not get means D3, derangement. 6 choose 4. So 4 got, 2 did not get. So 2. 6 choose 5. 5 got and 1 did not get. Can it happen? If 5 get, then it will get. So you write D1 also, you write D1 will be 0 only. And all got, that is just one way. All 6 got his own top quote will be just one way. And this is 0. That exactly 5 people, exactly 5 got his own It cannot happen. Exactly 5 got means 6 also must be good because everything is given. So it means this is just 0, no way. And exactly 6 is of course one way, that there is only one way. So you will add them. This is your answer. If you add this, this is the answer. Or you can subtract from total. You can subtract from total these two. 6 C1, this one, and D5. This one, then also you'll get the answer. But this is better, 3, 4, 5. So if number is big, then they won't ask you to calculate. They will just ask some series or something. So this is your thing for this one. That okay, one more let me do. Let me check what the result says here. I had one question in which I had the statement. Okay, this is one is this. This is IT example, very easy one. That 5 distinct balls. 5 distinct balls of 5 colors, 5 distinct colors, and 5 distinct boxes of same colors, of same 5 colors, of same 5 colors. This one. Number of ways to put balls into boxes. These balls only talked about. These balls into boxes such that no ball goes into a box of its own color. And then given that every box must have at least one ball. Every box should get exactly one ball. Every box getting exactly one ball. So it means 5 distinct balls. So that is say red ball, blue ball, white ball, then yellow ball, orange ball. So red, blue, white ball, 5 balls are there. And there are 5 boxes also of the same color. So call them boxes, you call them R prime, V prime, W prime, Y prime corresponding boxes. Now in how many ways it can happen that each box, of course, only one ball you have to send everywhere. In how many ways can happen that R does not go to R prime. So no box goes into a color of its own. So that is simple. That is just D5, no calculation to be done. Already we have done for formula, you know, it's all right. So this is D5 and D5 is 44. So it is number of ways 44 in which it can happen that this goes. So this is one, we do this kind of thing. Okay, so we will do tomorrow now.